After learning the uniform convergence of sequence and series, the question one can ask is what about the uniform convergence of power series? We know the power series is of the form an x minus x0 power n running from 0 to infinity. It is a series of function, and for certain values of x, this power series is convergent. So the question is, under which situation or under which condition the power series are uniform convergence? So for that we have a first theorem. So it tells you that under the radius of convergence, whatever the radius of convergence of this power series, we can say it is uniformly convergent, and we are just talking about the power series of the form a n x raised to n, because the same calculation can be done for any point x0, about x0. So this is the first theorem that we talk for the uniform convergence of power series, which tells you that if r is the radius of convergence of power series, summation an z raised to n, then for every delta greater than 0, 0 less than delta less than r, the power series summation an z raised to n converge absolutely, uniformly in for all z belongs to C such that mod z less than delta. So this is the first part of the statement, which tells you that if R is the radius of convergence, then under that radius of convergence, the power series is uniformly convergent. And the second part will tells you that if, since this power series that an z raised to n is a continuous function, and this power series is converged to a continuous function. That means since it is uniform convergence, and under the uniform convergence, as we have learned that the continuity is preserved. So then what we can say, the series summation an z raised to n represent a continuous function within the circle of convergence. Means that f of z, where f of z is a continuous function for all z is less than r. So the proof is very straightforward if we use the Weierstrass approximation theorem. What is Weierstrass approximation theorem? Let us recall that if you have a sequence of function which is pointwise convergent, and if fn of x is less than or equal to mn for all x belongs to R or C, And if the sequence Mn is convergent, then the series Mn is convergent, then the series Fn is uniformly convergent. This is known as Weierstrass approximation theorem, where you can have the sequence of functions, and this sequence of functions are bounded by a constant sequence Mn, and the series Mn is convergent, then the series Fn is uniformly convergent. Now here, what is given is R is the radius of convergence. So therefore, mode of Z is less than delta, less than or equal to delta for all delta which is less than R. We can say that mode of an Z raised to n is less than or equal to mode of an delta raised to n. Here R is the radius of convergence. So ultimately this is the constant sequence an delta raised to n, which is treated as mn. If I can prove that this summation of mn, which is this, is convergent, then we say that summation of an z raised to n is uniformly convergent. So we will show that summation of mode an delta raised to n is convergent, which can be easily done using the ratio test. Here, capital An is an delta raised to n, mode an into delta raised to n. So limit n tends to infinity, an plus 1 upon mode of an will give you limit n tends to infinity, an plus 1 delta raised to n plus 1 upon an into delta raised to n, mode of that. So this will give you limit n tends to infinity, mode of an plus 1 upon an into delta. But what is limit an plus 1 upon an, which is the radius of convergence? So that is delta upon r. Because r is the radius of convergence, the value of r is limit n tends to infinity, mode of an upon an plus 1. So an plus 1 upon an is 1 upon r. And this is less than 1 due to this condition. So what we can say, therefore, the summation mode an delta raised to n is convergent for all delta which is less than r. So therefore, by Weierstrass M test, we say that the series summation an z raised to n is uniformly, absolutely convergent. Why it is absolutely? Because it is the modulus is there. So that's why it is absolutely convergent for all mode z is less than or equal to delta, which is less than r. So that proves the part 1 of this statement. That is, the power series is uniformly absolutely convergent for all z which is less than delta. The second part, in that we have to prove that this f function, which is a limit function, is continuous. That is the objective, but which is continuous due to the uniform convergence. So what is in the second part, our claim is to prove that f is continuous on all z such that mode z is less than delta. Here, if you can consider fn of z is an z raised to n, is a sequence of continuous function because it is a polynomial function, and we know that every polynomial is continuous, so that's why this is a continuous. and summation of fn of z, we have assumed it is f of z. And we know that the uniform convergence preserves the continuity. So therefore, f is continuous for all mode z less than delta less than r. So that completes the proof of this result, which tells you that under the uniform convergence, the power series, sorry, under the power series is always convergent under its radius of convergence. And the limit function, whatever the limit function is there, which is always a continuous function. Now, we will have the another result. Actually, this is a lemma to use in the next very important results. In that, we are talking about the term by term integration and the term by term differentiation possible into the power series. So we have already learned results on how to do the term by term differentiation and the term by term integration in the series. So all those conditions should satisfy for power series also. So for that we have this lemma. It says that if the power series summation an z raised to n has a radius of convergence r, then the power series summation n into an z raised to n minus 1 summation an upon n plus 1 into z raised to n plus 1 have a radius of convergence r. So it says that if the power series has the radius of convergence r, then its derivative series, that is n an z raised to n minus 1, also have the radius of convergence r, and its integrating series, that is summation an upon n plus 1 into z power n plus 1, also have the radius of convergence r. This is easily proved using the concept of a radius of convergence. So probably you know this result is true for this statement is if an is non-zero for every n and limit of n tends to infinity, an upon an plus 1 is exist. Include being the diverge to infinity. Then the radius of convergence of the power series an z raised to n is r equal to summation integration mode of an upon an plus 1. Okay, this is the very well known things which we already know. Here, given that the summation an z raised to n has radius of convergence r, that is the radius of convergence. Therefore, the value of r will be limit n tends to infinity mod of an upon an plus 1. So our claim for the first thing, that is to prove that summation n into an plus into z raised to n minus 1 has radius of convergence. So 1 to infinity n into an z raised to n minus 1 has a radius of convergence. These are. So as per the statement, the R is limit of an upon an plus 1 due to this. So what is an here? Is n into an. That is your an, if you can consider. So you have to take what is limit n tends to infinity an upon an plus 1. That is limit n tends to infinity n into an upon n plus 1 into an plus 1. So this is limit n tends to infinity 1 upon 1 plus 1 by n into an upon an plus 1. This will tends to, that means this quantity will tends to 1 due to n tends to infinity. So this has the answer limit n tends to infinity mod of an upon an plus 1, and this is has the answer R. So which proves that summation n into an z raised to n minus 1 also have the radius of convergence is R. So therefore summation n an z raised to n minus 1 has radius of convergence is R. Or the other things that I am giving you as an exercise, that is the claim is summation an upon n plus 1 z raised to n plus 1 as radius of convergence is R. I am giving you this is as a homework. You can do it yourself. As we have did it here in the same manner, you can able to do this. Now the next results that is interesting, which you already discussed in your analysis 2 also. The statement is this: suppose that the power series fx is equal to summation n running from 0 to infinity an x raised to n as x belongs to R has radius of convergence R greater than 0. Then prove that the following. That is the first one. F is differentiable on minus R to R, that is that radius of interval or convergence of interval. And for x belongs to minus R to R, f dash of x is exactly the term by term differentiation is there, that is n into an x raised to n minus 1. And the second one, f is integrable on minus R to R, and the integration from 0 to x f of t dt will be summation n running from 0 to infinity an upon an plus 1 x raised to n plus 1. For any x, it is in minus R to R. Or I can say here it is 0 to R. So to prove the statement, we have to use the results which we have discussed for term by term integration and the term by term differentiation for the series of functions. So let us discuss the proof of this statement. From the above lemma, what we can discuss or what we have arrived is this series summation n into an x raised to n minus 1 and an upon an plus 1 x raised to n plus 1, both of them have the radius of convergence is r, and both of them, and the previous result says that if the radius of convergence is r, then these two series are uniformly convergent. So by above lemma, the differentiation series, I can say this is a differentiation series summation n into an x raised to n minus 1 running from 1 to infinity as radius of convergence r. Therefore, since this is a radius of convergence is r, the previous result which we have discussed that the power series has a radius of convergence is r, then it is uniformly convergent. So therefore, this series, that is 1 to infinity and an x raised to n minus 1, is uniformly converged in all x such that x less than mod x is less than delta less than r. So under this, it is uniformly convergent. And what is the term by term theorem for term by term differentiation is possible? Let us recall that statement. The statement states that for summation, first of all, Fn, each Fn belongs to the AB, which we have already here. This is your Fn here. And since the summation an x raised to n is your Fn, and each of them is a polynomial, so no problem with the differentiability. So each of this an into x raised to n is differentiable function. The second condition, summation of Fn x0 is convergent. That means for some value x0, for some x0, it is in domain. It has to be convergent. And the third condition is summation Fn dash is uniformly convergent. This is the third condition. Then we can have the term by term differentiation is possible. And this series an x raised to n is satisfying all these three conditions. The last condition is we have already done. We have already stated that is n into an x raised to n, which is the derivative series. That is the derivative of this is uniformly convergent. So that third condition is satisfied. The first condition is also satisfied because an x raised to n is differentiable. The second condition is also satisfied because for some point the series has to be convergent. So in particular, it is actually convergent for all points which are less than r. So we can say that the series summation an x raised to n satisfies all the conditions for term by term differentiation. So therefore, d by dx of fx is equal to d by dx of summation n running from 1 to infinity or 0 to infinity an x raised to n is same as summation running from 1 to infinity n an x raised to n minus 1, which is the derivative of that. So that completes the proof for the first statement. Now to do the second statement, we require just the series is uniformly convergent, because under the uniform convergence, integrability is you can interchange the summation and the integration sign. That also we have learned. So to prove the second part, we require just the series summation an x raised to n running from 0 to infinity is uniformly convergent for all x which is belongs to minus r to r. So therefore, the series summation an x raised to n satisfies all conditions of term by term integration, and hence the integration is possible. We will take the integration from 0 to x f of t dt is equal to integration from 0 to x summation n running from 0 to infinity an x raised to n dx. So this is summation n running from 0 to infinity an x raised to n dx, which is summation n running from 0 to infinity an x raised to n plus 1 upon an plus 1. So which proves the statement B, that term by term integration is possible for a power series.